Okay, welcome everybody. So we are going to look at even more examples of things to determine whether or not a set and some operations satisfy these 10 axioms that are required for it to be a vector space. So we've been working with vector spaces that consist of vectors, vector spaces that consist of matrices, and I want to take a look at, in this video, at a couple of vector spaces of functions. So for the first example, let's let our set V consist of all continuous functions that map from R into R. So we're thinking of single variable functions with the usual operations where we add two functions using the same way. We can group like terms and so on. And when we multiply a function by a scalar, then we distribute that scalar through every term in the function. So now let's consider these functions with our usual addition and scalar multiplication to see whether we satisfy these 10 properties. So the first property is if I take two continuous functions and I add them together, do I wind up with a continuous function? And here the answer is yes, since adding two continuous functions results in a continuous function. That is true, and we know that from calculus. That is a fact from calculus. Secondly is if I take a continuous function f and add it to g, is that the same thing as taking function g and adding it to function f? And yes, it is, because what comes out of these functions, the outputs are real numbers. So real numbers are commutative when we add them, so we can add these functions in either order. Does it satisfy the associative property? Yes. Do we have a zero vector in this case? We do. I'll call this z of x, would just be the function that is equal to 0. So if I add this to any other continuous function, right, it won't change the value of that function. We'll get the same function back. And this function, z of x equals 0, that is a continuous function. Do we have additive inverses? Yes, so for any function f, we can construct its additive inverse by multiplying that function by -1. And if f is continuous, then -1 times f, that is also going to be a continuous function. So we do have an additive inverse that exists inside the set V for any function f inside of V. Multiplying a function by a scalar, multiplying a continuous function by a scalar will result in a continuous function. So we're closed under scalar multiplication, and all of these properties, 7, 8, and 9, are just going to follow from properties of real numbers. And in question 10, property 10, if I take a function f and multiply it by the scalar 1, yes, we get back the original function that we start with. So this is a vector space. We have a vector space of continuous functions. Okay, so now let's take a look at the same set of objects as in the previous example. So V is still going to be all continuous functions, single variable functions that map real numbers back into real numbers. And we're thinking of just the continuous functions. We're going to use the same scalar multiplication, but now we're going to define addition of two continuous functions differently. Rather than add the two together in the typical addition sense, we're going to define addition of two continuous functions to be the composition of those two functions. So if I take f plus g of x, what that means to us is first evaluate g and then compose that, plug that result into the function f. And so let's take a look at these same 10 properties. So if I take a continuous function and I add it to another continuous function, in this sense, we're composing them, is the composition of two continuous functions going to be continuous? Is it going to live in V? And this is a result from calculus that we know that when we compose two continuous functions, the result is going to be a continuous function. statement 2, axiom 2 here is saying, is it true that this operation is commutative? So in other words, is it always true that u plus v is going to equal v plus u? So in this case, what it means here is it true that if I take and plug g into f, that is going to be the same function that if I change the order of that composition? This seems a little odd, and if you're thinking no, that is correct. And let's take a look at an example. So let's let f of x equal x squared and g of x equals x plus 1. Then if I take f plus g, that would mean I'm going to take the composition in this way. And in this case, I'm going to plug x plus 1 into f, which is equal to x plus 1 squared. If we were to take g plus f, that means we compose them in the opposite order. And now I'm going to take x squared and compose it with the function x plus 1. And so the first way of composing, right, we would get x squared plus 2x plus 1. We have this middle term when we distribute out this squared expression. When we compose them in the other way, we just got x squared plus 1. So since these two are not equal to each other, addition in this way is not commutative. And this is enough at this point, since we violated this, to stop and say this is definitely not a vector space because it is not closed under, or excuse me, because addition is not commutative. And I think it might be good exercise to go through and check some of these other properties to see which ones may or may not be satisfied. And I'll kind of just indicate them with green and red check marks. So anytime you see a check mark over here, this means that property 3 does hold, property 4 does hold. Anytime you see an X, that means that this property does not hold. And so one interesting thing to point out is what would the 0 vector look like? In this case, we do have a 0 vector, and that is going to be some function. In this case, it's just going to be the identity function that f of x is equal to x. And now when I compose any function with f of x, it's not going to change the operation of that function. And with this in mind, what property 5 is saying, is there an additive inverse? What that really means to us now, since we're composing functions, is for any continuous function f of x, does there exist an inverse function? And this is not true for all continuous functions. So for example, the function f of x equals x squared, it does not have an inverse function. So therefore, this property 5 is not satisfied. And you can check the results of some of these other axioms as well.